Okay, so first of all, thank you very much for inviting me for this nice program and workshops. So then, today I will talk on something related to turbulence. But some of my friends, US friends, said US speaker start his talk with a joke. But while Japanese speakers start with apology. So probably I have to start with some apology.
You just started with a joke.
And okay. As you already noticed, my apologies is that I have no distinction between L and R. So turbulence is the most difficult one for me to pronounce. Okay. So please be patient with my pronunciation, especially for turbulence. Oh, where is? Oh, it's strange, but it is.
I'll find one.
Okay, oh, sorry for that. Okay, so then, this is the work with my Japanese collaborators. Then some part of my application of my theory to stellar convection and atmosphere is on these journals. Okay, then today I have to talk about several topics in 1 hour or 15 minutes. So first I will talk about some introduction of convection conundrum. Yesterday, Nick already made a great talk about that. Then I can skip some part. And also then I will explain some my theoretical formulation.
They have a laser pointer here.
Oh,
They took away the.
I prefer this time.
We're not allowed to use that anymore.
Oh, okay. Then it's okay. Okay, then I will talk about my theoretical formulation. And it's a multiple scale direct interaction approximation. Usually it requires one semester to explain. But then I will also talk about non-equilibrium effect. What kind of non-equilibrium effect we will implement into turbulence model. Then also, in order to apply it to multiple plumes, we have to also adopt some filtering procedure, not usual ensemble averaging or something. Then I will present some model based on my theory, then apply it to stellar convection. That's my content today. So first of all, this part, yesterday Nick gave us a very nice introduction. Only the point is, I can say is that important point is that near the equator we have a prograde profile. So near the equator we have faster rotation in the case of the sun, and also we have information of meridional circulation. Still some open problem we have, but anyway. Then in the community of stellar physics, recently we have this convection conundrum. Not only the Tacock line Nick mentioned, even the convection zone itself, we have some puzzle. And it is nicely summarized by York Schumacher and Srinivasan. Okay, then roughly speaking, one is convection velocity amplitude at large horizontal scales is much smaller by helioseismology if it is compared to numerical simulation. As you see here, I really need something here. So helioseismology, this is a spectrum, this is a mode, and this is energy. So then helioseismology gives much smaller energy for the larger scales. That's a very important point. And second point is that if we adopt the solar parameters, then we will it's very difficult to reproduce prograde profile of differential rotation. It just gives the anti-prograde profile. And finally, thank you very much. Thank you. Much better. So, and the final point is that if we certainly have such smaller amount of energy for large-scale motion, how we can reproduce enhanced heat transport? That's the final problem. So then there are several approaches to this problem, especially the stellar physicists. Then one is the rotation effect. I think some part Nick already mentioned. And also magnetic field effect, which is related to turbulent Maxwell stress, effect of turbulent Maxwell stress. And today I will focus my talk on coherent motion effect. Okay? Then I myself has my own prescription for rotation effect through the kinetic helicity. Those who are interested in, please look at my recent book, just published from Wiley. I edited this book. And another point is that related to turbulent Maxwell stress, I think cross helicity plays very important role. This is my work in this journal, and today I will concentrate on this topic. Okay, then there are several works, not all, but I just feature some work related to stellar convection work. Then, of course, we have a very important contribution related to entrainment, related to plume motion. And Turner and Linden also. And also surface cooling, because of the radiative cooling. We have a surface cooling, then we have a strong plume motion. And people started to consider such plume motion plays very important role for heat transport in the stellar interior. There are several. And also entropy rain, and also for supernova explosion, people consider the importance of turbulence recently. Then entrainment is considered to be very important. So in this sense, plume motion, not only just super adiabatic convection, plume motion, they are considered to be very important for stellar convection. Today, later I will show this very nice setup for stellar convection. Later I will return to this point, but Mark Rust and his collaborator consider this type of things. One is everywhere super adiabatically by entropy gradient, we have locally convection is driven. And another case is almost all region of convection zone is marginally stable. But only the surface region, we have a strong cooling. So then they compare these two cases. And this is a result. This is we call it, this is a locally driven case. This is non-locally or surface cooling diving case. Okay, so this is a locally driven case, and this is a surface cell structure of these two cases. So as you see, locally driven case by super diversity is much larger scale of horizontal dimension compared to the non-locally driven case. And this is also shown in spectrum, in numerics. As you see, this is locally driven case. This is a scale. This is smaller scale. This is a larger scale. Then locally driven case, we have much higher energy in larger scales. And but surface cooling case, we have much smaller energy for larger scales, but larger energy for smaller scales. So in this sense, we have fairly different properties between the locally and non-locally driven convection case. And this is how to say, vertical cut. Then as you see, in non-locally driven case, surface cooling case, we have much more stronger plume motion compared to locally driven case. And one important point is that this is our result. If we plot a spatially distribution of turbulent energy flux or heat flux, this is surface and this is bottom. And the red one in this figure shows the non-locally driven case. And the blue one is locally driven case. As you can easily see, non-locally driven or surface cooling case, we have much more effective energy transport. And also which is localized near the surface where plume is located. Okay. And such difference cannot be reproduced by usual gradient diffusion model at all. Okay, this is the case. So for locally driven case, gradient diffusion with mixing length theory gives nice result. But for non-locally driven case, this is a mixing length theory result, not at all good, not at all good. So this is related to the third point of convection conundrum. So with not so much convection motion in the large scale, how we can reproduce this type of higher amount of energy transport. One of the goals of my talk is to attack this problem. Okay, I'm already exhausted. But then a theoretical framework. So we use response function with multiple scale analysis. And this is the work first. This is a classical modern turbulence theory started by Bob Krasner. Then this is called the direct interaction approximation. I'm trying to explain his work just two view graphs. Okay? Then he starts to expansion with Gaussian velocity fluctuation, but at the infinite past. So then anyway, we start somewhere. This is the velocity and this is a response function. Then we have, with expansion, we can write pictorially for me, this type of diagram is much easier to see. Then a velocity field is written by expansion, we can write something like this. And also response function equation, this is response function. This is the exact response function. And this is a bare, so-called bare response function. Then we can write down like this. And one of the very good point, I think, kind of genius of Bob Krasner is not only the velocity field and its correlation, he started to consider response function. It gives us the possibility to close the nonlinear equation without resorting to any parameter, like eddy damping or some tau approximation, blah, blah, blah. So then okay, this is just, but then finally, as you see, he used renormalization. Renormalization procedure is very roughly speaking, if you have an expansion 1 plus x, then in the case of Navier-Stokes, this x is nonlinearity related to Reynolds stress. So in this sense, this x is not at all small in turbulence. Then if we truncate somewhere here, then the result is not at all good. So that is what quasi-linear theory is doing. But if we take all terms, this is even partially, if we sum up all all the order of expansion. In this particular case, we just replace this with an exact one. This is a basic idea of renormalization. Then, in this particular case, we happen to have an exact result. So in this sense, previous one with bare propagator is replaced by exact one. Then we can solve the correlation function and Green function. This is the way he did it. Oh. Okay, but that theory is only for homogeneous isotropic turbulence. Then we expand it with multiple scale analysis. I have to skip the detail, but important point is we introduce the two scales, at least two scales. Then delta is scale parameter. If delta is very small, capital X and capital T are very nice variable which represents slow variation. Because only when original X and T changes large amount, then capital X and T start moving, start changing. So in this sense, capital variable is called slow variables. And Guzai and tau is fast variable, okay? Then all derivatives, spatial and time derivative is just written like this. This is just a consequence of introduction of two scales. The important point is that if we have a time derivative, it has this type of large scale variation in time with delta. And if delta is very small, we have very nice scale separation. But the delta is not necessarily small. Okay. So, but anyway, then all large scale inhomogeneity in space and time, and also anisotropy enters with delta. This is a basic idea. But as this result, original equation becomes much more complicated. Even solenoidal condition becomes something like that. But this is just algebraically, very straightforwardly calculated. Okay. And this is Bob Krishna. And this is my mentor, Yoshizawa. And you see, this is almost 30 years ago. And you see a very young guy just behind Bob Krishna. Okay, so but anyway, then we apply it to the Navier-Stokes equation in this particular case. Then as you see, all the inhomogeneity effect and anisotropy and non-equilibrium effect show up on the right-hand side of the first order equation. Then we can define a Green function for the left-hand side. Then we can formally solve first order field in terms of Green function and zeroth order field. Okay. Then we can calculate any order in principle, any order of turbulent correlation with this formulation. Then actually we use, and also we need some statistical assumption for the lowest order field. In this particular case, we just adopt homogeneous isotropy for the lowest order. This is a velocity and magnetic field correlation. Then this is the solenoidal part, this is the compressive part, and this is the helical part, which represent breakage of non-mirror symmetry. Blah, 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 blah. Oh, something wrong. But anyway, then we can calculate any turbulent correlation in this expansion. This is a basic framework. Then, for example, in compressive MHD case, we have to consider all these turbulent fluxes. Okay? And those who are interested in the expression and also very messy calculation. You can see my paper, JPP papers. Okay, then non-equilibrium effect. Non-equilibrium effect. There are several aspects of non-equilibrium property. Here, of course, any fluid system is basically non-equilibrium system. Then with a boundary and also fluxes of energy with motion and mass flux, fluid system is basically non-equilibrium. But here we just consider the deviation from the local equilibrium. Local equilibrium was assumed by Kolmogorov to derive some nice result. But due to our multiple scale analysis, written like this, we have velocity fluctuation. Temporal evolution velocity fluctuation has this type of term. This means that if we have some inhomogeneity, large scale inhomogeneity of fluctuating field, it can enter to the expression. This is a way how to implement non-equilibrium effect. I mean deviation from local equilibrium into the turbulent theory and modeling. Then again, we just focus on this term related to, in this particular case, Lagrangian derivative, advective derivative of fluctuating motion. Then, utilizing Green function, we can solve first order field like this. Green function coupled with this one. And for example, if you look at this part related to velocity shear, then multiply U0 here, then you will get Green function, U0, and spectral integral. So U0 part gives energy, and this part gives how much, this part gives time scale, basically, roughly speaking. So this gives time scale multiplied by energy. This is a, how to say, generalized expression for the mixing length. Tau, U. Okay. So in this sense, from the fundamental equation, we can derive some modeling expression of eddy viscosity type, and eddy viscosity representation itself is contained here. But here, today, we just concentrated on this part. Then as I mentioned, we can calculate any turbulence correlation. Here, we just focus on energy. The energy can be calculated like this. Then if we apply the previous stages formula, then this is an energy expression. So as you see, this is exactly the same one with the Kolmogorov expression. And the red part represents non-equilibrium effect. That means that turbulent energy itself should change due to such one. And then if we solve with respect to length scale, then by iteration, then again, this is exactly the same one as Kolmogorov expression. Then all other terms represent non-equilibrium effect. That means that if we have non-equilibrium effect, we have a deviation of length scale from equilibrium state.
Sorry, can I interrupt? When you say non-equilibrium, you actually mean unsteady, not simply not. I mean, the difference between the blue Kolmogorov stuff and the stuff with time derivatives is these are actually non-stationary, is that right?
Non-stationary,
not merely not equilibrium, but not stationary.
Yeah, that's right. Okay, actually, they are represented by the energy variation and also dissipation rate variation. Okay, not only energy, but also dissipation rate dependence is very. Then, if we just approximate this part like this, so in this sense, this quantity is very important. K square over epsilon, which is usually related to some transport coefficient, Then, how much it changes along the large scale motion. or mesoscale motion, or plume motion. How much is this going? Then we just consider like this. Then already that type of argument has been done for the homogeneous shear flow. Homogeneous shear flow is just we have a homogeneous shear flow. But the usual K epsilon model, I was a bit surprised, but referred several times about K epsilon. But anyway, K epsilon. So then it completely failed. Even this type of very simple flow, because this is non-stationary. Then this is DNS result. Once we start at some moment K epsilon, apply K epsilon, it gives divergence evolution of K something. So in this sense, even this type of very simple flow, K epsilon fails completely. But if we add this term I mentioned, which gives nice agreement. Of course, we have one model constant and additional term. This is very natural, but better than this agreement. Okay, this is a case for application to. Then related to plume motion, I just consider recent, I think, Los Alamos people, I think, round jet experiment. They exactly measured this quantity. Then this is this quantity k square over epsilon along the jet direction. Then, as you see, we have some decreasing tendencies. In their paper, they said this is almost flat. But for me, this is certainly decreasing. That means that we have some non-equilibrium, deviation from scale similarity. Usually, entrainment argument use scale similarity. Then, but as this experiment clearly shows, simple jet case, we have some deviation from the equilibrium state. That means that deviation from scale similarity. Okay, then in my quantity, this gives some minus 0.7 something, this quantity. Then, which agree with the tendency engineering people has to increase the model constant from 0.09, which is related to Kolmogorov constant, but people need to increase it to optimize. Okay, and another one is buoyancy bubble plume case. The same argument can be done. I will skip that part. Then I would like to apply this non-equilibrium effect to the multiple plume case. But if we naively, previous one is just one plume, then still we saw some deviation from equilibrium. But if you we'd like to apply it to multiple plume situation, in such a case, we need some additional technique. That's a double averaging procedure. Okay, so then there are several possibilities. Actually, I consider how to implement intermittency and also conditional averaging and also a kind of wavelet analysis, how to extract information of coherent motion, coherent fluctuation motion like plume. But I found, at least in my case, these approaches didn't work well enough. Then I just adopted this type of double filtering. And filtering approach is very actually essential part of the subgrid scale modeling. In this particular case, I wrote some Gaussian filtering or sharp cut filtering. Anyway, then the point is that some part of large scale turbulent motion, large scale AD is solved. Then unresolved part, which is called subgrid scale. should be modeled using the resolved grid scale quantity. That's the basic idea of subgrid scale modeling. But people also consider double filtering. It is so-called dynamic Smogorinsky procedure. In addition to one filtering, they also apply second filtering. Okay, then extract some information of unresolved scale somehow. That is a typical double filtering approach in subgrid scale modeling. This is very ubiquitous for data analysis. But in my case, I apply double filtering in time domain and space domain. This is the way how to extract information of plume. Then we first apply time averaging, time filtering. Then F bar and F double prime. Then apply space averaging. Then all field quantity is mean flow and plume and random noise. Okay, this is a basic idea. As this morning, Pat said, this is, I think, 3 animals problem in this sense. We have three animals. But anyway, and in this particular work, we just adopt the very simplest possible time filtering. This is just the simplest possible work. But of course, as you can imagine, how to choose T, time averaging window is crucial point. And to my knowledge, there is no general way to determine this one. We need some additional physical insight to determine this one. Later, I will return to this point. Anyway, then, okay, so I'm already running out of time. Then we have some rules of averaging. Some of them are exact, some of them are just approximation. But if we adopt this rule, then we can write down the equation for example, Reynolds stress for, tilde is coherent fluctuation. And double prime is random fluctuation. Okay, then we see the terms. And then as you see here, we have exactly the same equation for both, but the opposite sign. This contributes to just the transfer of stochastic. And in the case of energy, much simpler. As you see, we have, as the usual case, if we have shear coupled with a kind of Reynolds stress, we have production mechanism, pressure dilatation, and dispersion rate, and buoyancy effect, and transport terms. This is very usual as for each component has such one, but this one gives just energy transfer between coherent and incoherent energies. So then I think this is very important, but in my work I have not yet considered much on that. But then this is the scenario, as I mentioned, we have some energy transfer mechanism between the incoherent and coherent one. Okay, then by cooling at the surface, the plume got some kinetic energy, then start going down, diving. Then with this energy transfer term, it may give the energy to the random motion. Of course, depending on sign, we may have inverse transfer. But then this is the situation. Then if we just, this is again approximation, just modeling. If we adopt very simple eddy viscosity type model for random fluctuation, then in such a case, this production mechanism is written something like that. So then depending on lambda, it may enhance or suppress the energy transfer. Then if lambda is negative, we have enhanced energy transport from coherent plume to the random motion. that point is clear in this argument. Okay, then utilizing such averaging procedure, we can model a turbulent heat transport and mass transport and also momentum transport. Then finally, I will apply this result, and probably this is some numerical setup. Then I will skip that part. But we just consider the polytropic gas and the equation of state we consider. Okay. Then this is the so-called Schwarz-Zito condition. Then if we adopt a ratio of gamma like this, then 1.5 is marginal one. Specific heat ratio. Okay, then in our calculation, Rayleigh number is just 10 to the 6. But mass ratio is 100. In this sense, very big mass ratio. Then this is the result. So first of all, time evolution of kinetic energy is in saturated state. Both are very similar. I compare the locally driven case and surface driven case. So energy itself is the same. But the spectrum is, as Mark Rust already showed. So non-locally driven surface cooling case, we have much smaller energy in the large scales. And this is the structure. So this is much larger and this is much smaller. Then here we have very dominant plume. In this, then this is a coherent magnitude of coherent fluctuation. And again, such quantity is basically depend on how much averaging T we adopt. Then depending on T value, it changes. If T averaging time is very long, it just gives a very similar profile for locally and non-locally case. Then again, this is T. Then we just adopt T with some physical arguments. Then lifetime of plume and averaging time. So non-dimensional horizontal is about something like that. Then so we just approximate it as just a crossing time. Then it should be something like 20 something. Okay. Then if you adopt 20 something, we have a much large coherent component. And this is a key quantity. How much turbulent energy alters along the mesoscale motion, plume motion. And as you see, this is the surface, this is bottom. We have very large, in the case of 20 something like this. So we have very localized non-equilibrium effect represented by this. Then this is almost the final result. Then by DNS, we have again very much higher heat transport compared to locally driven case. Then, as I mentioned, it cannot be reproduced at all by usual gradient diffusion with mixing length. But with this non-equilibrium effect, agreement is good enough. So in this sense, I am happy. But this is just because we add one additional term, and also with model constant. But again, better than disagreement. Okay. Anyway, so in this sense, non-equilibrium effect may be a promising prescription for stellar convection problem. Okay, this is, I think, final slide. Okay, so as I mentioned, first I used some methodology of multiple scale DIA. And utilizing DIA, renormalization, we can treat strong nonlinearity. Okay? And also, using multiple scale analysis, we can treat inhomogeneity, anisotropy, and non-equilibrium effect. Then I focus on non-equilibrium effect here. Then, applying such formulation, we need some additional averaging procedure. That was time-space averaging. Then we extract some information of the plume. Then we use some plume motion information to express heat transport. In this sense, this is large AD simulation. So we use the resolved scaled quantity to express unresolved transport. Then it works so far. Then it was good. But my intention to be here is that I would like to much more consider about the physics of plume formation. Because I just argue about if we have a plume, then how much it affects turbulent transport. But, and as you already noticed, my plume is just something. So no special, how to say, no distribution in scale, no distribution of speed, no distribution of all this aspect ratio, blah, blah, blah. I just represent such effect. So what determines the non-equilibrium property of turbulence in this particular case is a main type. And also this is a probability distribution function for downflow and upflow, comparing the local case and non-local case. And for upflow, we have a very similar profile of both, but downflow case is very different. So in this sense, there is some information. And also this is heat fluxes, and this is a scatter plot of the vertical velocity and heat transport. So in this sense, we have some, not linear, but probably this type of, I think this is a cubic profile or something. I have no idea. But these points should be explored much more. Okay, so thank you very much for your patience and attention. Thank
you. Great, thank you. Right on time. So I can't resist, I'm going to get in trouble here, but I can't resist listening to all this story with you know, DIA and all that one more time, and thinking about the rest of the meeting. I'm wondering, have you considered something like a Bly approach to this problem? It seems to me you've got two regimes. You've got a normal regime, which is the usual crap, and you've got a strong transport regime where you have a long mixing length. And I mean, it just has Bly written all over it to me. And one would guess, shooting from the hip, that the strong regime might be something like a flux-limited diffusion model, but that's just a guess. But you might come to the same thing with a few hundred pages less of algebra. Have you thought about an approach like that?
Yeah, okay, so thank you.
Sorry, but I mean, it's so obvious in this context.
I fully understand your point, I think. That point, it's very difficult for me to answer. At least I can say, even with this type of, how to say, approach, we can get some result. Right. We could get some result. But as you know, I'm actually what is missing in this approach is validation of theoretical formulation itself with some numerics. Only I can say is that some result derived from such several hundred pages calculation gives some result which is in some sense consistent with the results. That is the only I can
I'd argue for Occam's razor, but just, it's just a comment.
Yeah. I appreciate your point, and that point I should be always in my mind.
But his model is related directly to the PDEs, right?
Yeah, but I mean, you could argue so is, Y is just a K epsilon model recognizing the two scales,
Yeah. And also, K epsilon itself is originally based on equilibrium.
Yeah.
And the epsilon is called dispersion rate, but it is just energy transfer rate. Then we have to consider such energy transfer rate. What kind of energy transfer rate we have for turbulence we are considering. It may be drift wave turbulence, it may be Navier-Stokes. Navier-Stokes case, we have, happily enough, we have some constant epsilon. This is the assumption of column follow. But still we have a deviation from that. And how about in the case of drift wave turbulence or blah, blah, if you would like to use K epsilon type argument for such turbulence modeling. That point
Yeah, but I mean, that's been done.
Okay.
With the usual caveats, but, if you, just to hold my ground, they're buried bodies in the DIA too. It's just there's a lot more stuff buried on top of the buried body.
Okay.
All right.
Phil, can I make a comment on
Yes.
this comment? Okay. So starting with Bob Pregnant, so you started making moment models, getting like a BBJKY expansion, and you needed a closure. So he was clever enough to say, let's do the closure with renormalization, okay? And so, that was then picked up by people like Victor Yahout and Steve Orzog, and they went through your 100 pages of algebra, and what did they get at the end? They got the K epsilon model for homogeneous isotropic turbulence. And everybody said, well, that's really great. Why bother to do the 100 pages? But so I think it's great that then you're doing kind of a due timing on this to look and see what you're going to get. So I would encourage this.
Actually,
As long as he does it.
Actually, when I talked, as you know, when I talked, we'd like to do this with your formula to Bob Krishnan. He said to me, crazy, you are crazy. So, but he's a character. I think it's his own way of encouragement for challenges. I'm very optimistic.
And other questions? I'll ask one actually. So does your modeling approach say anything about why you get a coarser pattern in the one case versus the non-local forcing case?
Not yet. That's a very important point. In order to do that, we have to much more seriously consider that.
Okay.
Yeah, that point. Yeah.
Thank you. Oh, yes, Dave.
Can I just ask you about the convective conundrum that you
Yeah,
put
yeah.
at the beginning? You said that the observed flows are not as strong as one would expect from numerical.
Yeah.
From global convection.
This is
Yeah.
This is discrepancy between observation and the numerics.
Yeah, but okay.
Nothing to do with theoretician.
No.
But anyway.
I'm just trying to get to the bottom of the conundrum. I mean, the global convection simulations, of course, are a million miles away from the sun. So why is there so much faith that there is any conundrum?
I'm not the person. Probably Nick can. Yeah.
I mean, why might you just not say that the global convection simulations are not modeling the sun. I mean, that's perfectly reasonable, because how can you? But why is there so much faith that we should believe the global convection simulations have something to do with the sun?
But even with very rapid progress of numerical power, it's almost impossible to.
Of course.
Of course.
Of course.
At least within my lifetime. Then we need some modeling. So then, my hope or my wish is this type of argument I presented can contribute to some modeling. Oh, yeah, but I'm the last person who can answer your question on that. But yeah, as I mentioned, so people just start to for example, Maxwell stress plays very important role, something like that. But such point we know already 30 years ago, or much in advance, we know, and theoretically we have such expression. So in this sense, progress of numerics is still very slow, I think, in my viewpoint. Then Nick has some.
I was just going to comment a little bit, is that, I mean, it's true, you're massively in a different part of parameter space than you want to be to do solar actual simulations. And you would hope that you get some really, really basic, large-scale effects correct, though, even with, lower Reynolds numbers than you need. So, for example, the thing is, with the convective conundrum is that to even get an equator that rotates faster than the pole, you have to have a certain type of rotationally influenced convection to do that. You need these sort of banana cells, thermal Rossby modes, whatever you want to call them, fairly large-scale things around the equator. And in the sun, you don't see these things at all. So that's the thing that everyone's worried about is that if you stray away from that in the global models in any direction, you don't even get a fast equator and a slow pole. So are we getting that completely wrong? That's what everyone's worried about right now.
Well, with that thought, let's bring our session to a close. Thank you again.